A support vector machine, SVM, is a type of supervised machine learning classification algorithm. SVM were introduced initially in 1960s and were later refined in 1990s. However, it's only now that they are becoming extremely popular owing to their ability to achieve brilliant results. SVMs are implemented in a unique way when compared to other machine learning algorithms. In this video, we will see what support vector machine algorithms are, the brief theory behind support vector machine and their implementation in Python's scikit-learn library. We will then move towards an advanced SVM concept known as kernel SVM, and we will implement the kernel SVM as well in the coming video.
Now I am going to give some more clarity on hyperplane. See, we already discussed about hyperplane, so I am going to give you some more idea on what exactly is a hyperplane. A hyperplane is a decision plane which separates between a set of objects having different class memberships. If you see here in the figure, I have marked here. This is two types of data sets. Here you can see one is marked red in color and the other one in blue in color. You could see here we have come up with in the right hand side figure, we come up with an optimal hyperplane. You can see here that's the optimal hyperplane. In the left side you have multiple hyperplanes, but the optimal hyperplane we have seen in the right side. And you have the maximum margin. See, some of the data points in the in the margin, near to the optimal hyperplane, having the maximum margin as the width, that's shaded. You could see here the red points and the blue points, it's shaded there. Those data points we call it as the support vectors. See, support vectors are the data points which are close to the hyperplane. These points will define the separating line better by calculating margins. That is the maximum margin. It's shown in the figure. These points are more relevant to the construction of the classifier. If you want more clarity on this support vectors, see, it's marked here. Here we have shown the margin width, and you could see some data points which is coming in the margin width. We call it as the support vectors. Fine. Now I am talking about what is this margin. I am talking about the margin width. What exactly is margin? See, a margin is a gap between the two lines on the closest class points. This is calculated as the perpendicular distance from the line to support vectors or closest points. If the margin is larger in between the classes, then it is considered a good margin. A smaller margin is a bad margin. Now we are going to discuss about the working of SVM, how support vector machine is working. So that's what I am going to discuss now. The main objective is to segregate the given data set in the best possible way. The distance between the either nearest points is known as the margin. We already discussed. The objective is to select a hyperplane with the maximum possible margin between support vectors in the given data set. SVM searches for the maximum marginal hyperplane in the following steps. First step, if we discuss about when we talk about the first step, generate a hyperplane which segregate the classes in the best way. Left hand side figure, if you see the left hand side figure showing three hyperplanes, black, blue and orange. Here the blue and orange have higher classification error, but the black is separating the two classes correctly. The second step, select the right hyperplane with the maximum segregation from the either nearest data points as shown in the right hand side figure. So we have selected the black hyperplane. Next point you need to understand here is the nonlinear and inseparable planes. How do we deal with nonlinear and inseparable planes? See, when the data sets are scattered like as shown in the figure, how do we handle such situations? Some problem can't be solved using linear hyperplane. See, whatever we were discussing was linear hyperplane. See, as shown in the figure left hand side, the linear hyperplane on work. In such situation, SVM support vector machine uses a kernel trick to transform the input space to a higher dimensional space as shown on the right hand side. The data points are plotted on the x-axis and z-axis. Z is the squared sum of both x and y. Now you can easily segregate these points using linear separation. Now we will understand different SVM kernels. See, what is SVM kernels? The SVM algorithm is implemented in practice using a kernel. A kernel transforms an input data space into a required form. SVM uses a technique called the kernel trick. Here the kernel takes a low dimensional input space and transforms it into a higher dimensional space. In other words, you can say that it converts non-separable problem to a separable problem by adding more dimension to it. It is most useful in non-linear separation problem. Kernel trick helps you to build a more accurate classifier. There are different types of kernels you can use. One is the linear kernel. See, a linear kernel is used when the data is linearly separable. That is, it can be separated using a straight line. It is one of the most common kernel to be used. It is mostly used when there are a large number of features in a particular data set. A linear kernel can be used as a normal dot product of any two given observations. The product between two vectors is the sum of the multiplication of each pair of input values. You may be aware of that. Next is the polynomial kernel. A polynomial kernel is a more generalized form of the linear kernel. The polynomial kernel can distinguish curved or nonlinear input space. Here in the equation, d is the degree of the polynomial. When d is equal to 1, it is similar to the linear transformation. The degree needs to be manually specified in the learning algorithm. Next, we need to understand radial based function kernel, that is RBF. See, the radial basis function kernel is a popular kernel function commonly used in support vector machine classifications. RBF can map an input space in infinite dimensional space. Here, gamma is a parameter which ranges from 0 to 1. A higher value of gamma will perfectly fit the training dataset, which causes overfitting. Gamma is equal to 0.1 is considered to be a good default value. The value of gamma needs to be manually specified in the learning algorithm.